In this video, we will learn the performance indicators of a complex reaction network. The performance indicator of a single reaction was conversion. Conversion is an indicator if we are dealing with a simple system in a single reactor. Still, we can estimate the conversion in a complex reaction system as well, but our indicator is not going to reflect the conversion in each of those reactions. Conversion is an indicator for a reactor, but not for the individual reactions that are taking place in the reactor. When we have more than one reaction, we have to also identify in which proportion these reactions went towards production and how much of the feed is used to produce our desired product. So we have to define the terms such as desired and undesired product. The desired product in this reaction network is methanol. And the undesired product is water it is consuming our useful reactant, which is hydrogen. Okay? So, the conversion can be defined for the principal reactant. If we look at the net reaction, or if we have chosen to write this reaction in terms of carbon dioxide, we could have said defined conversion for carbon dioxide. In this case, we can write the conversion for carbon monoxide or hydrogen. Let us write it for hydrogen. Right? It is involved in both of those reactions. So instead of CA0, we can write CB0. I'm going to skip the symbolism, but I will define the selectivity and the yield. Selectivity can be defined in terms of overall selectivity and instantaneous selectivity. And why we define as overall and instantaneous selectivity will become more relevant when we are solving problems in a plug flow reactor or in a mixed flow reactor. Selectivity is the amount of desired product formed per reactant reacted. So let me correct the conversion in our particular reaction for B, because it is our principal reactant in this reaction network. Selectivity is the relative amount of desired to undesired product. So C minus C0, how much of C formed per mole of CE minus CE0. if we are measuring concentrations, if we are measuring number of moles, we can define selectivity as NC minus NC0 for a batch reactor divided by NE minus NE0, or we can define that as the molar fluxes Fc minus Fc0 divided by Fe minus Fe0. So these are overall selectivities. I measure the amount produced at the end of the reaction, compare it to the amount that I have put into the reactor in the beginning, and so this gives me the overall selectivity. This is the overall selectivity. Then we define the instantaneous selectivity, and it is related to the rates. R D over R U, the rate of the desired reaction to the rate of the undesired reaction. This is the instantaneous selectivity. We have to define one more term. We have defined conversion. We have defined selectivity. We have to define the yield of the reaction. Yield gives us how much of the reactants that are converted are used to produce the desired product. So it is, in mathematical form, it's conversion times the selectivity, or it is the desired product C minus C0 divided by CA0 minus CA. So much is converted, so much is converted. How much of this is used to produce the desired product? So these are the performance indicators of a complex reactor operation. We will use conversion, selectivity, and yield, and we will optimize our design, choosing, for example, conversion as our key performance indicator, or choosing selectivity as our key performance indicator, and we will optimize the reactor operation, design and operation for that.